Good evening, everyone. Welcome to week 8. It's so nice to see you again. I guess since we've last talked, the exciting things that have happened are that you have submitted assignment 2, which, as I said in my notice, is super cool because, you basically have done 40% of the course already. Um, uh, Whereas, in a lot of other courses, students are still working on, or have just submitted things that are worth smaller percentages. Um, and basically, the good thing about where C++ is at is that we're at the tail end of a course that is quite front heavy, in the sense that the rest of what we talk about in this course is not really to do with assignments so much as it's just a mix of general knowledge and the exam. So week 8 and 9 we talk about kind of relevant topics for the exam, and then in week 10 it's just a bit of revision and other stuff. So we're really getting to the easier end of this course, which is super helpful. But what we're going to be focusing on today is probably this topic here, which is advanced templates. Now, these aren't the most critical topics in the course to get. If you don't make sense of them, that's manageable, in terms it's not going to destroy your life. So the pressure's kind of a little bit off, a little bit in this area. Then tomorrow we talk about some more advanced type stuff, and we will probably talk about assignment 3 tomorrow night as well, because the next lecture is pretty light. Firesin says, how long does auto marking take? Auto marking, I'm not sure what you mean. We spend 2 weeks marking your assignments. I'm not too sure what your question is, but feel free to elaborate if you want. So, 8.1, advanced templates. This topic is all about taking what we learned at the start of week 7 with templates and basically expanding on it, so that we, how would you put it? The week 7 was really just about the basics of how you use it. Now we're really going to push it to the edges of what you can do with templates. Oh, I don't have a Y screen on this one. That's okay. Let's get straight into the action, I guess. I mean, the reason we're learning about this is because there's lots of actual use cases of dealing with templates where you want to do something quite obscure, whether it's templates of templates or default members or specialization. And if you know those, you can really make the most of templates. So one of the first things that we're starting with, for instance, is default members. And this is essentially default types for templates. And this one's relatively straightforward in the sense that if we pull up this code, I would hope that by now all of you will be familiar with sorry, all of you will be familiar with how, when it comes to functions, you have parameters for functions, right? And in most languages, those parameters can have default. How would you put it? Those parameters can have default arguments. You write a function in C++ or in any language, and you can say, int function, int a, int b equals 5. You can do something like that. That's pretty manageable. With C++, we can do the exact same thing for template types. So, for instance, inside of demo 801 here, you can see that I've got this class stack, which is just a stack class, and you can see that it takes in 2 different types. So remember that anytime we're templating either a class or a function, the line above is always template and then something inside the brackets. In this case, we've got 2 template arguments. We talked about this briefly last week where we said you can have a class that's templated on 2 different types. So this class stack is templated on a type name t, and it's also templated on a type name cont. So cont and t refer to types at compile time. But in this case here, cont is actually going to be, by default, equal to a standard vector of t. So what we're saying is if someone does not supply a type of cont for us, then we'll just assume that it's a standard vector. So essentially this is saying that we're building a stack where the container is a template, is like templatable in terms of this container here could be not just a standard vector, but potentially a standard list, or whichever are applicable containers that would compile. So in this case, if I tried to build and run this one, and we ran it, it works, right? Like it prints out 1 and 3 because in this case here we created a stack of floats and we created a stack of ints, and these both worked, and it set the default stack type to be a standard vector because that's what we did. So that cont type here was populated as a standard vector of type T. Now, if we wanted it to be a different type, we could of course simply say that by saying actually our stack is going to be, the elements themselves will be floats, and the container might be a standard list of floats. And then I'd have to include list here as well. Cool. So then when we run that, we get the exact same thing. Now, here's a question that I want to ask you all, and I want to see what your answer is what containers would and wouldn't work when it comes to like this code? So we just saw that a standard vector worked. Would a standard would and a standard list work? What other types would and wouldn't work here? I'll just wait for the lag to catch up. So Firesin says, would it depend on what functions are run in the .h? Alwyn says maps wouldn't unordered. Suresh says maps and sets wouldn't work. Now, the simple answer here, I mean, we can try this out, right? Like, what is an unordered set? Is it just unordered set? I think we just include unordered set. Let's try this one. So what would happen if we had an unordered set of floats? Unordered set of float. 801. Oh, this did compile. This compile and ran. So I had a few people saying, these things wouldn't work. Now, the simple realistic thing here is that cont can initially be anything you want it to. We could make it a Euclidean vector. So at compile time, so Firesin says, would it crash if you ran a specific function? So in this case, have a look at what this .h file is. This .h file is just a series of a constructor, destructor, and a default definition of a static variable, and then a whole bunch of member functions for this class that are not defined. But it doesn't matter that they're not defined because they're not even used by the caller in our main function, and therefore they're lazy instantiated, which means they're never actually created. Yeah, the result did change. Sorry, you guys are right. Well, okay, so just to be clear, the result here changed because... Okay, so let me talk about why the result changed in a sec. And it's back to what we learned in week 7 about static. So basically here, because these were lazy instantiated, they were never created. And there was actually no function in the definition of this stack that used the container. And since there was nothing that used the container, there was nothing to fail at. But for instance, if I define this type here, where I say, okay, we've got this container, and when someone calls push, I then say do, stack dot push back item, right? So someone calls push with a reference to an item. So for instance, here I do, whereas this one's ints, I say int j equals 5, and then I say is1.push j. So I want to push 5 to this stack. Now, what's going to happen here is that I got clearly a compile error somewhere. Sorry. So what's going to happen in this case here, right? Oops. What's going to happen in this case here is that this will also work because in this case, we are creating a stack of ints and standard vector of ints. Okay. This is working because when this particular data type goes to get instantiated, it's getting created with a standard vector of t's, of which pushback is a valid function call. Whereas watch what happens now if I try and do something such as fs, or, I could make a float. I'd say float k equals 5, and then I'll say fs dot push k. So now we get an error here because what's happened is that our unordered set has been successfully, we've created this stack, say. Think of this like compile time in slow motion. We've created a stack with an unordered set of floats as the container. The compiler's happy with that. It doesn't mind that. But then the second that it actually starts to try and instantiate this class, and it instantiates all of the functions that it uses of that type, which in this case is push, it now fails because it was like, you told me the type of stack was a standard unordered set of t, but then you called pushback on it, and I simply can't find this, right? No member named pushback in the unordered set. So there is no like kind of hard rules of what you can and can't do. It's like a lot of other things. It's a lot like the operator less than, where, how would you put it? With the operator less than, what happens is that your type doesn't need to define operator less than unless it actually like uses it. So it's the same thing here. It's like, what's a valid container? Well, it depends what you use. And back to the question about would it crash if you ran a specific function? Would it crash if you ran a specific function? It doesn't crash, it fails to compile, right? And I know that might have been what you meant. But yeah, that's kind of the gist of where that went. So that's what this case is here. And to point out that Jingheng says the result changed, and the result did change, and the reason for that's really interesting because previously when I had just had float of standard vector t like this, right? When I had this and we printed out here the stack float num stacks is in this case 1, because when I ask the compiler, when I tell the compiler I want the stack float type, right, what that actually is a stack float of standard vector of floats, because that's what I specified here as the default. So when I say when I just say stack float, this is implicitly standard vector of float as well. That's actually what that is in reality. So therefore it printed 1 before when I did a stack float or a stack float standard vector float, but the second I changed it to this, it was a whole different type. And what did we learn last week in week 7 about this is that every single separate instantiation in terms of types has its own set of static members. So in this case here, what that means is that if I was to say, maybe let's make another one, I'll make a couple of these. I'll make fs2 and I'll make fs3, and fs3 can just be a stack of float, is that if I try and say print out the, what is this here, unordered set, the number of the stacks, the reference count basically, or I print out this one, we will get 2 different values, and we'll get 1 and then 2 and then 3 we should get. Let me get rid of that. We get 1 and 2 and 3 because there's 1, the number of stacks for a float with an unordered set container is 1. The number of stacks for a float, which is the exact same as a float and the standard vector of floats because of the default template argument, is 2 because we created 2 of them, 1 here and 1 here. And then the number of stacks for ints is 3 because we created 3 there. So that's pretty much it on default members. A lot of it's maybe a little bit weird, but certainly not the least unintuitive thing you ever heard. But this leads us on to specialisation. Okay, so this is one of the biggest topics with templates we deal with. Specialisation is where we try and take the very broad definitions of templates we've had so far, which is basically saying I'm going to create a type and it's templated on these types like T and U and V, and they can be anything we want. And we say, let's make it more specific. And in particular, the two types of ways we make it more specific are partial specialization, which is where, you might have a generic type like a standard vector, and then you go away and you create another similar type for just say a standard vector of pointers of T's instead of just T's. That one's a bit confusing. And then you have explicit specialization, which is like, okay, I created this very kind of complex function for this complex generic type for a standard vector, but now I'd actually like to define a separate behavior for a specific type. And if that sounds a bit conceptual to you, think of it like, you might have a function like int min auto A, auto B, right? Or say auto something like this. Now, you wouldn't really do this, but you could say return, A less than B, A else B. Okay. Now, if you want to, like you could think of this like a generic function. Again, you wouldn't really want to use autos for stuff like this, but it's like, okay, this is me trying to generically describe a behavior. But if the behavior you want needs a different implementation for a specific type, you would do what you call specializing something, which in this case could be, say, for instance, auto min standard string A, standard string B, forget the references and consts, except in this case, imagine that strings, they should be sorted by size for some reason. So you say, return if A.size is less than B.size, return A, otherwise B. So in this case here, you have kind of specialized or given like a specialized case of how to deal with the min function, which is, that's all it really is you've got your generic case and you've got your special case, your specific case. So that's what explicit specialization is. And we're going to go through examples of both of those together. So the first thing is, when should you specialize? And I know this is a bit early because you probably don't even know what I'm talking about. When should you take something generic like this and create special cases for it like this? The times that you want to do that are pretty much only when you need to preserve the existing meaning of what something does, except if you don't implement something else, it would not work otherwise. So the point of specialization is not to create different meaning, it's to preserve meaning. It's like if you've created a stack that works on any type, ints, floats, standard strings, or whatever, and has the exact same meaning on all these types, you can totally generalize it, but then you need a specific implementation for a specific type. That's when you do that, to maintain that semantic. And we'll come back to this slide in a bit. In fact, maybe let's just talk about the examples and then we'll kind of come back to the why, because I think that'll make some more sense. Okay, so firstly, here's a stack template, very similar to what we looked at before. This one has its member functions defined. It has a push, top, pop, size, and sum. Sum is just defined using an STL algorithm, standard accumulate, where accumulates from the beginning to the end with 0 across the STL container. This one has a concrete type of standard vector for the container. So this particular type is just a stack of some elements, just like a standard STL container has. And then on the right, we've got our main function where we created two ints. We create a stack of ints. We add both of those ints to the stack, and then we print out the stack size, top, and sum. I feel like I might have had these examples somewhere. Anyway, this is like a standard stack template class. You should be familiar with this from week 7, right? Partial specialization is where we take a class like our stack and we make another template for it that's essentially saying, I want to deal with a special case of this, which is typically pointers. There are more cases in this, but we don't really go into them much in the course. But essentially what we're saying here is that maybe I want my stack to behave the same for pointers as it does for, say, ints. And let me like really spell this example out because it's probably a little bit confusing. Right, so Um, this is the full code example, which will make a bit more sense. So firstly, pay attention to how I've got my stack up the top. Push, top, pop, implementations, definitions, whatever, size and sum. Then underneath, I have another redefinition of that stack, except this one, I've actually had to specify here that it's a specific specialization of that stack. Basically, what this is saying here is that this is a templated type on type name T called stack. And this one here is saying this is a templated type on type name T where it's like stack, but it's only for T pointers. So now we're expecting only T pointers to be passed in. So when we call it partial specialization, the reason it's called partial is because if it was no specialization, if it was just a broad example, that's what we have up here, where it's just a stack that can take in anything. Whereas this one is specializing in the sense that it's doing something more specific, which is that it's only working on pointers. But the reason we call it partial specialization is because it's not a concrete type. Like T star is still could be anything. Like, it could be any kind of pointer. So that's why it's called partial specialization. And you can see here that the implementation actually looks really similar. One of the only differences is how we do the accumulate. But in terms of like top, pop, size, these things are all just like taking off the stack, pushing onto the stack. They're either taking a pointer off the top or they're pushing a pointer to the stack. So this stack is taking in pointers, right? So you have a stack of ints or you have a stack of pointers to ints or whatever. But you see the one thing that we've done differently here is that we want to preserve the sum semantic, right? And what I mean by that is that if you have a stack of pointers to ints, pointers to anything, when someone says sum on that stack, you still want to sum up the actual elements it points to. So in this case here, your stack's actually full of it's a vector of pointers. There's no real, summing up pointers doesn't make any sense. Like, you can sum up all of the values that those pointers point to, but you can't actually sum up pointers. So in this case here, the actual implementations for the, most of these methods are the same, but the implementation for sum is a bit different because now when we accumulate from the start of the stack to the end, and we start from 0, we have to give it a lambda to essentially tell it how to sum things up. Because otherwise the default behavior of the compiler will be to try and sum pointers. And you'll see this, right? If I get rid of that for a sec, and I try and run my code, it will try and use the one template I've defined. So when it tries to create a stack of ints or a stack of int stars, it will try and just use the same template because normal templates can be any type, right? They can be ints, int stars, int vectors, whatever. And you can see that I've got a compile error here because it's saying incompatible pointer to integer conversion. This is all because of this sum line. So you'll see if I get rid of this line, this all works fine now. This all works fine now, but once I sum it, because my container is a bunch of ints, when it tries to do this, it's like, okay, I'm going to start at int 0, and then I'm going to start trying to accumulate and reduce or sum up the elements, but each element's a pointer, so it fails. So that's why we need this partial specialization. And this partial specialization gives a more clear behavior of what to do with pointers, which is that add the running total to the dereference of the item I have in the stack, because my stack is yeah, cool. So now that's really it. That's like the whole thing. It's like you're pretty much just defining a special case. Sometimes, like when we say partial specialization, you might think, okay, is that just pointers, right? Which is like, it's like standard T star, it could be standard vector of T, whatever. Like, it's any time you're saying that there's a specific constraint that I'm adding to this, except that specific constraint is not a fully realized type. It still itself is somewhat generic. Yeah. So that's what that T star is there. Are there any questions about partial specialization? I think there was a question before that's like, do we need to write two separate classes? Yes. I do think you need to rewrite things from memory. Like you have to copy and paste. It's not really a very elegant thing. Let's try it. Let's get rid of the top function and see if it still complains, because we use that in the special case. Yeah, so it's basically like it doesn't exist. So it is a little bit of ugly boilerplate. This is one of those things that I imagine in future versions of C++ they will streamline substantially to avoid this kind of repetition. Yeah, any questions about this before we move on and maybe talk about explicit specialization? Oh, sorry, I missed your question. Did I miss your question, Alan? Oh, no, I think I answered that anyway. Yep. Cool. So, basically, explicit specialization is the exact same thing, except you're actually making it a concrete type. Right? So, with explicit specialization, we can try and do this ourselves here. I don't know if you say template type name t. I think you get rid of the template type name t from memory. No, template. You get rid of the type name t. My bad. So, the idea here is that if you're defining this for a concrete type, then you have this template type name t, except there is no t anymore, right? Like it's still an explicit specialization of a template, but there is no type name t anymore. So now, instead of this, we actually give it a concrete type, which here might, let's say we have a stack of standard strings for some reason. And now we, instead of push here, it's just, standard string t, and then the t here, similarly, like we just go and actually, make them all concrete. We get rid of the t's as the standard vector of t's, and then let's just start off with like this. So this is an explicit specialization because all the t's are gone essentially. There is no template or there is no type variable here. And what that means is that we can then come along and say, okay, well, actually, I'm going to make a new stack of standard string, and I will, say auto s equals standard string hello, like that, and then I'll say s3.push s, and we'll see if this compiles. Now, oops. What did I do wrong here? Yes. So one of the weird things about templates is that I'm pretty sure that when it comes to partial specialization, like, so this will compile, right? Let's just get a base case here. Oh, no, it doesn't. What have I done wrong then? Oh, okay. Yeah, so do you remember how back in week 7 we talked about lazy instantiation, which was that for templated types, the functions themselves, the compiler ignores the member functions unless they're actually used, right? Like if they're used, the compiler looks at them. And Nathaniel was in the chat, and Nathaniel pointed out that this can actually lead to some really weird behavior whereby, let me comment out my string class as well. I can really make this point clear. Nathaniel pointed out there's some really weird behavior here, how like, this program works, and if I get rid of this sum here, right, this function could fail, right? So this function may just say not work. Oops. This function technically right now wouldn't work if we tried to use it, but it doesn't matter because we didn't try and use it. And whilst we didn't try and use it, the compiler doesn't even bother trying to compile it, because if it's not used, how does the compiler even know whether it's valid or not? And we saw this before when someone asked, we were talking about, is this valid? And the answer is it depends what type you have. So if you have a valid type here, it works. It instantiates it correctly. If you have an invalid type, it doesn't work. And even if you have an invalid type, It doesn't even bother to check if the function works unless you call the function. That's all like just the template behavior. So templates behave a little bit differently than to our explicit specialization, because even if I don't create an instance of the class, even if I don't use a function in this class, and then even if I don't even create an instance of it, this is basically treated like a non-templated function at compile time. And this makes sense, right? Because the main reason the compilers don't instantiate something is because it doesn't exist. They don't know what type it is, therefore they can't do their normal checks. Like, you can't create a class of a type you don't know what it is. Whereas with an explicit specialization, you know exactly what it is. It's a stack of standard string. So in this case here, it's like, okay, well, I know what it is. Cool. I can check. And it did check for us. It checked and it ran this function. It knows what these types are. And it said this does not pass our type checking. Right? So 0. Sorry, not 0. So compile error. And the compile error here is exactly like a similar thing we had with the pointers, where it's like, I don't know how you want me to add a string to 0, because accumulate is adding all the values in the vector, and it's like, I can't add a string to 0. In this case, it's saying there's an invalid operand to a binary expression, which is adding int and basic string, which is, you know, the standard string. So again, for explicit specialization, we could define a separate lambda that says, say, I'm going to sum up all the string length. So I might copy this lambda here, just for simplicity. And this lambda, what this lambda does, it has no capture. It takes in the int, which is the sum, and then it takes in the standard string, which is the element, because all an accumulate does is has like a running total, which it's like always just adding onto. So this standard string is what we add to it, and in this case, I'm just going to add b.size. I just want to add the size of the string to the running total. Now this should compile, or get close to compiling. But b.size is an unsigned long. This is a bad example, by the way, so I'm going to do some really ugly things, and I don't even know if it's going to let me. It's probably going to complain. It's going to be like, use of old style cast. Okay. This example is meant to show you what not to do, so I was like, I'm not going to like overinvest in getting it right. Let me just word wrap it. Where's word wrap on this thing? Oh, word wrap. Toggle word wrap. Yeah. Oh, maybe this won't even work. Okay, so this one still works, and then if I tried to print out, notice how it didn't compile even though like we didn't even use it. And now if I try and print out, say, s3.sum, we should get the sum of the string, which is hello. So we should get 5, right? It's the wrong one. Is it? No, it's the right file. Okay. So we get 5. So again, because it's a string, we went to the explicit specialization. And the way the compiler works is that it looks for like explicit ones. Well, I mean, the compiler's just looking for an exact match, right? It always wants to do that. Then it'll look for a partial one, then it'll look for the most general one. So it moves in that order. Now, what I want to point out here is that this has mainly been me just trying to show you the behavior of this language feature. In reality, what I've done is kind of terrible. For partial, it's probably not great, but for strings, it's even worse, because what I've done here is I have changed the semantic of what all of this means. Now, it's maybe not the end of the world, but it's like the point of specialization is not to make your template work for every single type in existence. There are lots of types. There are templates that just might not work for certain types. You know, and there are conditions on some types you have to pass into templates. Like sometimes they have to be ordered types. Like if you pass a type into an ordered set and it doesn't implement an operator less than, it's just not going to work. You know, if I tried to create if I came into my code here and I was like, I'd like to create a standard set which is ordered of a stack of ints, the compiler here is going to say, sorry, but stack of int is not ordered, and I expect an ordered type with these kind of, you know, abilities, so I'm just not going to compile it. So, and that's totally fine, because like the aim of specialization, again, is not to make sure things compile all the time. It's not to just keep adding in all these random use cases so that things work. It's that if you know you can make something work the exact same way without changing any meaning, i.e. the person using it thinks it works identical, then do it, otherwise don't. So in this case here, I've kind of changed the meaning in the sense that this sum function should just not really work with string. Perhaps you could implement this explicit specialization to just remove the sum. Sure, that's okay, because you haven't really redefined the meaning of it here. Taking something away is probably better, but the main point is that you should just use this with caution. Okay, because again, back to the slides, whatever I set up here, you specialize to preserve existing semantics that would not compile if you hadn't made the specialization. The times you don't specialize is pretty much when you think it would be cool to change some feature for a class for a specific type. That's just a different class. If it has a different behavior, it's a different type. Otherwise, you're just an a-hole, really annoying people. So everyone will always assume that any templated type has the exact same behavior and semantics, generally speaking, for all these different types. That's like a good rule to follow. And the only other note on this slide is not to use template specialization for functions. As we've already talked about this before, like we don't really want you using specialization for functions anyway. We'd rather you just use function overloads. So yeah, just do function overloads. You don't need templates for anything like that. Phison says, so if the template works for type A, you don't need to make a partial specialization for type A. Yeah, exactly. So like if your class, like when you make a class like a vector, it has a meaning. That meaning is you can push, you can pull, it does this, it does that. If it works for all types, then you don't need to specialize anything. But let's say for some reason, your template doesn't work with pointers. Something breaks. I'm not too sure what. I don't use a ton of partial specialization, but it just doesn't work. And you think, well, if I just implement this differently, I can bring it to the exact same meaning as something else, so that other people using my thing won't even know. It'll look the exact same. But in reality, I've had to, pull some levers and make some things a little bit different. An example that I don't know too much about, though I thought it was really interesting to read about, I linked something here about standard vector bools, and I actually think that's did I miss a point? One sec. Oh yes, the only thing I've missed here is that another reason for specialization is if you have like a templated type like a vector that does compile with, say, a string, it is fine, but you think you have a way to make things go faster. And an example of that is with standard vector bools. And I don't know, like, I'm not 100% sure on all the details here. I read this and kind of mainly went through this a year ago, but even if I'm missing something, or even if I got pranked or something, I'm just kidding. But like the point is still the same, is that I mean, here we're looking at it now. For space optimization reasons, the C++ standard calls out vector bool as a special standard container where each bool only uses 1 bit of space rather than 1 byte. Now, what do we know about memory with computers? We know that a byte is defined as the smallest amount of addressable memory on a computer. So like, yeah, you deal with bits, but you can't update a bit on a computer. You can update bits that are part of a byte. Like you say, this memory address points to this byte of memory, and you can update that byte, which consists of those 8 bits, right? But as you know, like a bool, a true or false is just a bit of data. So like, there's no point, like when you store a vector of bools, say, and you got your byte over here, which is, like 10101011. This is 8 bits in a byte, and you're trying to contain a huge amount of data, like potentially 2 billion or whatever integers. But is it 2 billion? I can't remember. But if you think about it, like if you have a standard vector of bools, oh, that's a 4 byte in. I'm sorry. It's like a char, right? It's 256. I'm a moron. So let me take a step back. 1 byte on a computer is like 256 pieces, right? A char is 1 byte. Say a simple char that can do the ASCII characters as 1 byte of memory. It can do 256 values. So when you have a standard vector of chars, it's going to be smaller than a standard vector of ints, right? Because a standard vector of chars is going to be, 1 byte for each character in the array. A standard vector of ints is going to be 4 bytes for each item in the array or vector, right? So a standard vector of ints with 10 elements will be 4-ish times bigger than a standard vector of chars because of the type. The problem with bools is that bools use less than 1 byte, right? Because even though chars use 1 byte, that's because they need to represent 256 characters, which means they need 8 bits. So they need 8 little pieces of binary. A bool just needs 1, true or false. So when you have a standard vector of bools, if you just store it as a standard 1 byte data type, then you're essentially wasting, 8 times the memory. Because in a single byte, you could represent 8 bits. You could represent 8 bools. So an example, and I've never had to interact with this. I just think it's an interesting academic example. An interesting example of this point up the top here about there are one of the other reasons to specialize is when there's an optimization you can make for a specific type without changing the semantic is standard bool. The idea that you could implement standard bool as a bit map or a bit set or whatever, so that each kind of byte, holds 8 bools or something like that. So you could do this for, say, space performance reasons. So storing a vector of 1 billion bools uses 8 times less memory. And this a lot of this stuff starts to make sense, which is one of one thing I like about C++ is here we're saying, with this specialization, since you can't get an address of a bit, which makes sense because, like on a computer, let's say that you're storing 16 bools. Those 16 bools might be across 2 bytes. So you got 1 bool, 2 bool, you got 8 bools here and another 8 bools here. You can't actually access a particular bool. You can't say, go get me the 3rd bool or the 5th bool because a computer can only interact with the start of each byte. So the Stack Overflow page here is describing, since you can't take the address of a bit within a byte, things such as operator subscript, which you're familiar with because of assignment 2, can't just return a bool reference because typically what you do is you return a byte, a reference to a particular piece of memory. So instead, standard vector actually returns a proxy object. So maybe an intermediary class or something. I know very little about this in the details. Because I don't really care that much personally, but I think it's an interesting, again, academic example about how you can use explicit specialization to actually give an optimization. So standard bool would work fine. It still compiles without an explicit specialization, but if you do this, then you can maybe get a type that looks and feels and behaves exactly the same, but can have some potential space performance improvements. Cool. That's pretty much it on specialization. Just having a quick look. A few things. Let's quickly talk about type traits before the break. Type traits are a really interesting example of explicit specialization or even partial specialization, and they're probably a way we can help really solidify what the purpose and usefulness of some of this stuff is. You might have seen these things before. These things around where you can get some information, or I don't know how you describe it. Whenever you see something like this in your code, it's what we call a type trait. And a type trait is essentially a type in C++ that characterizes a type, as in gives you some information about a type. And the really interesting thing about type traits is that they're actually just implementations. They're actually just explicit specializations of a particular templated type. So, for instance, have a look at the bottom code here, the struct numeric limits. This is a true generic templated type in C++. It's a class struct, they're all the same thing. It's a class type called numeric limits, which has one public static member function, which is min, and it returns a type t. That's what min returns, and yep, and it's not implemented, it's not defined, right? And what that means is that if you tried to go and instantiate a version of this, just generally, if this was all that was declared, you would not be able, the compiler wouldn't do it. It'd be like, sorry, there's no definition there. But what we're doing instead underneath is we're actually creating two explicit specializations of that numeric limits type, one for ints and one for floats. And what we're saying is that for the int explicit specialization, my static function min is actually going to return me this particular value, which is kind of defined at the like int max is like, think of it like a global variable that's tied into the specific compiler you're using that knows what type of operating system you're on, because on different operating systems your integers might be different, right? And, you know, same with like float max. So it's like you can actually get the limits of the biggest int and double you can get this way. And again, one really powerful thing about this is these aren't runtime checks, right? These are actually compile time checks where the compiler can actually bake this in to your code. Like when this all gets compiled up, this entire line here just simply gets replaced with int max -1, or a function that just returns that, for instance, if it's not const expression. So really powerful, because it means that, you know, you can kind of you can define the limits of all these primitive types just by simply doing explicit specializations. And it's a nice little abstraction. It's, you know, again, you can const expression this and reduce it all to just a constant at compile time without having to memorize anything. This is part of the limits library here. But yeah, that's super cool. So that's an example of a type trait, because this is characterizing a type. In this case here, the characteristic is the numerical limits of a particular type. Now, other reasons type traits can be useful, right? Well, not other reasons. Reasons type traits can be useful is if you remember back to our non-type parameter examples from week 7, the start of week 7, we talked about how you can non-type parameter a find max function for, say, a standard array or something. Which will have some compile time benefits and all this other stuff. But one of the problems with any kind of standard function that finds the min or the max of a list of values or an array of values is that whenever you're finding the min or a max, you generally either need to set the min as the first element, or you need to set the min as like some massive number, so that pretty much anything except like any next value is going to be smaller than it. You've probably done something like this before, right? Where you said the largest number, or well, sorry, I've got that the wrong way around. Where you've said the largest number is negative 9,999,999, right? Minus 9999999 on the keyboard, right? You're like, let's just make it the smallest number possible so that literally any number in our list is going to be bigger than it. That's a good default value, because, you know, it's just easier. As you can see here, now instead of doing that negative smashing 9 on the keyboard, we can actually just say that the largest number so far is the literal minimum that this type T can be. And the benefit of using type traits instead of just saying int min, or importing some random C++ library that has that constant defined in it, is that because we have these type traits, which are templates, we can actually generalize what the minimum is now. So we don't even have to, like, whether that's int or float or whatever, it doesn't matter. Our find max class, or function, sorry, is able to put in that type. Like, for instance, if you do a find max of an array of ints, then it will just call the numeric limit on int. So the cool thing about all these things is that it really allows you to build these really consistent layers of abstraction where your function and other type traits it uses can all be templated on the same types, because all these systems are using the same kind of template structures. Pink Omega says, don't we need to make it a const expression to make it compile time? Yeah, so I think there's some examples we have somewhere, but these would need to return const expression values to, at compile time, be like injected directly in. Though the main benefit of this is not, like, I kind of alluded to that at the start, so that's probably my fault, but the main benefit of this, as you see it, is not necessarily performance. It's actually just a really nice abstraction. It means that, like, because of type traits, you can simply say that I want to find the maximum of this type t, whatever that is. And to start off, I need to find the minimum value of this type t, whatever that is. So when someone comes along and they add a new type, say if they wanted to a C++ library, they could just add not only that type, but they could add an explicit specialization for the numerical limits of that type and define the min, and therefore it all keeps working with the same infrastructure and processes and stuff. There's a couple more examples of type traits here, which use both I'm really off it today. Partial specialization and explicit specialization. And this is a really good example of partial specialization. And when I said earlier, like, I don't use partial specialization much, what I mean is that I've never come across a situation myself where I've needed to partially specialize a class that I've written. But I understand like how it's used in the library. So a good example of other type traits are, say, is void, which is another templated class, which simply has this so is void is these are really sneaky ways of doing things, which I really like. Is like you create a templated class called is void. All it has is a static const bool that's false. So there's a static data member that's just false. But you explicitly specialize it for the case of bool to have that data member be true. So now, when you have a program like this and you say standard C out is void val, is void of an int val or is void of a void val, this one's going to print false and this one's going to print true. And you might ask, what the hell's the point of that? Cool, we just printed out whether void is a void. That was helpful. And a lot of the reason, I'm not sure if I have an example, we have an example on the next slide, is like, I like to think of this as it allows you to capture type traits as values. And I know it might sound weird to you, but it's like, you don't write programming with types. Like, you don't put types in your if conditions or your while loops. Like, all of those things are all values. So if you can convert a type characteristic to a value, it means you can do logic programming with it. It means you can say for a templated type, when someone instantiates like here's an example. I'm pretty sure there's probably another type called like is bool, right? So it's like you could for instance in your code say something like I've got my templated type up here, my stack, and I could say here if is void, let's start with that, is void t val, then I'm gonna like deal with the void case, else I'll deal with like the non-void case. So it actually allows you to add some conditionality to your code based on the particular type that's been passed in, so that you don't have to like necessarily even explicitly specialize things, but you have a little bit of conditionality there, which is nice. Now, the more clear examples of that are, and I like this example, demo 807, which is like, we have a main function that creates, an int, a long, and a double, and then we have this test if number type function here, where we basically just want to see if it's a number. So we just have a function, we take in a value, and we want to see if that value is a number type. And what we're doing is we're actually using type traits here to say, okay, well, my test if a number type is a templated function, sorry. This is actually one area where like, this is probably like one of the few examples I can think about where a templated function is better than an auto function, because with an auto function you couldn't really do what we're doing on line 6. But the point here is that I've got this templated function that takes in a generic type t, could be any type, and then we simply say if it's an integer type or it's a floating point type, then we're going to standard C out that it's a number. Else we're going to standard C out that it's not a number. So we're using these type traits to capture the generic type that ends up getting constructed and extract traits of that type. We don't know whether t is an integral or not. We don't know whether it's a floating point. It depends on the type that the person using your library actually ends up calling, but this allows us to build this conditionality into it. Are there any questions about any of this? I'll wait a minute for any questions and then we can take a break. Phison says, will it mostly be for static functions? Probably the most common case of partial specialization I've seen is for um, uh, static. Well, like not static functions, just like these library types that are mainly like static's just a way it manages this because you're not instantiating anything. You're just dealing with a struct. It could technically be a function as well, I guess. Also, I glossed over this example before, and I'm sorry about that, but this is the example of partial specialization, where here I actually use a partial specialization to determine whether or not a particular type is a pointer. Um, so again, this is a value. This is a value you could put in an if statement. You could say if value. You could actually in your template, like you could do this with your graph in assignment 3, right? You actually put something in that's like, yep, if the type being passed in is a pointer type, and I'm going to use that type trait. I think this is missing. These might be missing some STDs. Oh no, sorry, we custom made these. My bad. Yeah, so like this would help you figure out whether it's a pointer or not in a nice generic abstract way. So let's take a 5-minute break and then we'll keep going through and we'll talk about Variadic templates and member templates and some other things. Yeah, so I'll chat to you in I don't know 5 or 10 minutes. Cool. We're gonna keep moving on. The next real topic to chat about is Variadic templates. This is a bit of a random topic, I'm not going to lie. We don't really know where to put it. Could probably put it in tomorrow's stuff, to be perfectly honest, now that I think about it. But this whole week 8's kind of where some topics ended up, just generally. There's more of that tomorrow. But Variadic templates are a really interesting example of something you can do with C++, particularly around templated types. And even more importantly, it plays into some stuff we'll probably talk about with standard forward tomorrow, which I find very confusing, as you'll soon find out. But the idea with variadic templates is it's basically, you got to think of it like, I think of it like type recursion, in the sense that, have any of you ever wondered how, say, I mean, this isn't the best example, but like, have you ever wondered how a printf can just take any number of arguments? Like, you can give a printf like the format string and then however many variables exist. You give it like 100 variables or 2. How does it deal with all of that? Has someone manually gone and written in like var1, var2, var3, var4, and then defaulted them? Like, how does that all work? So there's some kind of variability there in terms of how those functions take in arguments, right? And a simple way that we can do that with C++, in fact, we could implement our own print function, is to template a print function, just type name t. I think of this like the base case in a recursive sense. It takes in a reference to a const t message, and then it standard couts that message. And then we make another templated function, which is still called print, which takes in 2 things: a type name a and a type name b. But these kinds of dots refer to like a list. It's like a spread operator. It's just a way of saying many type names, like many type names b. And then when we look at the actual function parameters itself, it's saying that we're going to take in 1 argument, which is our head, and then we're going to take in the rest of our arguments, which are tail. So tail here refers to a type that is a collection of b's, basically. And this is referring to here as a type that's like a collection of b's. And then we print the head, and then we call print on tail ... which is like the collection of b's, which may recursively instantiate another version of print. Because again, like, think about how if this is kind of confusing, think about how printing a linked list works. You give it like the head and then the rest, and you print the head, and then you recursively call print on the rest, which prints the head and the rest, and you kind of go you go down that path until you eventually run out of things to print. So therefore, if I try and print 1 and 2 as a float, it'll work. If I try and print 1, 2, and hello, that'll also work because it can like recursively deal with it. What's really interesting though, that I think helps make sense of what's happening here, is that let's have a look at the instantiations that are generated. Yeah, I'm getting Prolog flashbacks. I haven't looked at Prolog since 2013 when it hurt me. Do you know Claude? You know Claude? UNSW? You know, Claude was like one of the. I'm probably wrong about this, but Claude was one of the people that helped write Prolog, or part of it. He was a big part of Prolog. I don't know much. You should go email him and ask him. It's probably written here. Where is it? Prolog, or is it somewhere else? Prolog. I don't know. Maybe I made that up. Maybe I dreamt it. But yeah. Don't know. I should ask him and remember, so I don't either butcher his work in either way. But anyway, we have cool people at UNSW is the point. I don't. He was a very relevant part of the community in its early days. That's about as broad a statement as I'm confident on. Yeah, he's a smart guy. Leads up the AI group, I believe, or robotics or intelligence. I'm not sure what they call it. The intelligence group. Anyway, smart, very smart guy. So I just lost my train. Yeah. So what's interesting here is that when we actually do something like these two print statements, there's a whole bunch of instantiations that are generated. And again, this is actually one of those random things that also makes C++ quite a fast language, because a lot of it's kind of compile time. In the sense that, like, if you had a language like, I don't know, Python maybe, and you say you print many things, like, think about how Python works. It does like all these like runtime checks. Like, it's like, oh, I have a list of things to do, like my KW args, and I'm just going to go through them all and figure out what all, like, there's a lot of runtime checks that happen. Whereas what actually happens with C++ is that when you say, I want to print, I'm just double checking. I think this on the right here is just the bottom one. So like these are the instantiations. I'm probably saying it weird, but these are the ones that are created when I call print with one as an int, two as a float, three as a char, a pointer to a const char, which is a string literal in C, right? Is that firstly, when I call this, it tries to generate this function here. So what I want you to visualize is that when you call this, when the compiler sees this function call, it looks for a print that's types match this. It finds this one, the Variadic template, and it generates this piece of code in the binary, in the executable. So, and this makes sense because basically what it's like is like, I'm going to take a type A, call it my head, and I'm going to print the name associated with that type, and then I'm going to go take all the other things and print those next, which is why we get kind of print BC. I might have explained that poorly early on, but it's like that's the gist of it, is it's like it just groups them together. In other languages, the spread operator is a way to kind of capture in other languages, a spread operator is a way to take a list of things and essentially break them up as if they were like normal parameters. So instead of the second print getting a single argument, which was a list of stuff, it's actually getting all of those things you had as separate arguments. So we end up having print A and then print BC. But then the compiler says, okay, print A. Well, I don't know how to print A. A is an int. So the compiler then looks at this and it says, that's not a template I want. And it looks at this one and says, oh, that's a good template. It takes in one argument. We can match it. So then it instantiates this one here. Right? It instantiates that. And then it looks at this print and it says, how do I print B and C? I don't have something for it. It goes back to here, which works. And then it instantiates this one, which is the head and then the tail. Right? The head of type A and the tail of like the list type-ish B. And then it does that, but then both print B and C, printing a float and printing a pointer to a const char, they both need their own functions. So again, we get two instantiations of this. Richard says, are you saying that the print functions on the right are created at compile time? Exactly. That's exactly what I'm saying. So what actually happens here is that all of these different function calls are statically resolved. Now, is this a good thing? Maybe, probably, but you know, sure, it's going to add some code bloat. But again, the reason we like some of these languages like C++ is because they're very fast. Because now at runtime, there are no checks. It's literally a series of function calls. It's as if you just define these all yourself. There's no, you're not dealing with polymorphism, you're not dealing with anything strange. It's just here's the list printed out, the exact functions, make the calls, do the stuff, go, go, go. So that has some benefits to it, of course. But it's just kind of relevant to understand how it works. Are there any kind of questions about that? Otherwise, we'll keep going. I'm gonna go. Keep moving. One of the last few topics to talk about is member templates. So clearly this could work, but doesn't by default. Yes. So let's look at this code here. What we're trying to do is we're trying to create a stack of ints, and then we are trying to push to that stack, and then we're trying to create a second stack of ints, and then we're trying to create a stack of doubles that takes in a stack of ints. Okay, so what are member templates? Member templates are essentially functions or member functions of a class that deal with other kind of templates. So, and this again, this isn't something that's like you're going to use every day. It's just an understanding of how the language works. So firstly, when we tried to copy construct it, this works because we know that if you don't define those rule of 5 things, the compiler will generate them for you. It'll generate the copy constructor and the move constructor and the copy assignment and the move assignment. And it'll just do a member-wise copy for you. So if you do this, the compiler will automatically generate a copy constructor that will simply copy all the members across, and standard vectors copy constructor will copy all of its members across, and you get that big, beautiful, recursive copying. But this one here won't work when I try and construct a stack of doubles with a construct of ints. And that makes sense because it's not a copy construction, right? That's actually kind of like a boutique function, or it's a copy constructor with a specific kind of argument. So member templates are a bit weird, but the idea with member templates is that if you have a class like this, a stack, you've got a constructor, you've got a push, a pop, an empty, all those things you'd expect. It's full of vectors. You've got your pop implementation of it. This is from week 7. And then you use it like this. If you want to be able to do this and construct a stack of doubles given a struct of integers, then you have to start doing some funny syntax things like this. And what this is you saying that actually inside my templated type, which is templated upon type name t, I want to create a copy constructor, or I guess this is specifically a constructor, that takes in a stack of another type or a reference to it. So obviously if I was, let me look at the code, let's look at the code together. Obviously if I was just saying like I want to create a copy constructor, then you could probably do something like this, right? I have a, and maybe make it const as well. I want to create a constructor for my stack. It takes in a const reference to another stack of the exact same type. But if we want this to be a different type, then we need to put template type name t2 above it to kind of specify that no, while this is a generic class and this is a constructor for a generic class, it's actually taking in a separate different type, different generic type as part of the parameter list. And then from there, the only other weird thing you need to keep in mind is that when you go and implement that outside of the class, let's say you want to define it underneath to keep your code a bit cleaner. In a normal case when you're doing that, just like pop, you just write template type name t up the top, just like your class. And then you just scope it just like a normal class thing we've learned in week 3. This is what we learned in week 7. But if you're ever doing member templates where you're not only defining a constructor for a template of type, but that constructor is using another template of type, such as say taking in a stack of another type, then you actually need to put both template type name t and template type name t2 above it. Now, you can't do template type name t type name t2 because that would imply that this particular function is templated onto like static types. That would actually be a whole different type. That's a different thing. What we're saying here is that we're dealing with 2 templates. Both of them have one generic type in them. one of them's our stack and the other one's the other kind of stack. And you can see that the way this function actually works is that, and by the way, this one is something you probably wouldn't want to do because there's some problem, like there's some best practice problems with like having a stack randomly unload its values and cast. I guess it's an upcast at least, which is good. But yeah, you can go through the old stack of ints, and then you could push it to the new stack and statically cast them to T, which is the type of the new stack. So that's essentially how you could do some generic template programming between your template of type and another template of type. Yeah, so that one's kind of interesting. That's pretty much it on that. Are there any questions about that? I'll give you guys 30 seconds again for that one. Richard says, so a copy and swap idiom there would be better if that's even possible. Yeah, it would, but the two problems with this example, in my opinion, are that one, well, I mean, this example's main problem is that it's operating on a stack. And I don't know how much you'd want to allow moving between different types for a copy constructor. This is just an easy example to kind of explain some intricacies of the language's behavior in quite a small amount of space. But yeah, normally you probably wouldn't use a separate type. I think it'd be pretty normal to, define a copy constructor just with one type. Jin says, can you explain the template T2 thing again? Are you referring to like when I brought this up and said it could be this? If you are referring to that, my point is that that's just like a different thing. It's like giving it a different function name. Like the second stack's templated on two types. It's a different. It's saying that my stack is templated on two different generics, like my object. Whereas something here is more saying that my stack is templated on one object, one type T, but it's going to be using another object of another template of type T2. So it's just the difference between saying I am two things versus like there are two things. Like instead of saying there's one thing with two types, we're just kind of saying there's two things with one type. Kai says, is there a way to specify a constraint or what template type it can take in? What kind of constraints do you mean? That'd probably be the question I have most on my mind. Because like you can obviously, like if you only want it to be one type or two types, you could constrain that with some specialization. A lot of that's kind of handled for you implicitly, I guess, because I guess as a library writer, you don't really care what type it is. That's the whole point of generic programming. You just need to make sure that that type has the fundamental capabilities that you expect of it. So, for example, in in your graph assignment, you assume that the types are ordered, I believe, because you need to be able to sort the edges. So, so yeah, in a way, like that's constraining it implicitly. It's maybe not that well documented, and you kind of find out about it through a compiler. But generally speaking, it's like if it compiles it, the type's good enough. I can't imagine situations where you would want your templated class to not work on a type that is valid. If that makes sense. But I'm not sure. There might be something I'm forgetting around the constraints. This one is probably one of the more interesting and confusing things. And there's a few different ways to do this, as we've learnt in previous terms as well. And this is the idea of template parameters. And template parameters are simply saying that, like, with a template, you're saying that this class has a template type, and it has two type parameters. One is a type T, and the other one might be another type T, or maybe there's only one templated type parameter. What a template parameter is saying that I've got a template with type name T, but then the other type is actually another template with type name something. And I'm not going to lie, this syntax weirds me out and I never remember it. And if you asked me before this week to do it, I'd just be randomly trying different ways that the templates and type names work, because it's just like an overload of like template type name, which is a little bit weird. And I can try and explain to you how I think about it. But basically what this is trying to do is, if you think back to our earliest example today around default, you probably noticed, and you might have been thinking about this, that when you create a stack of floats with an unordered set of floats or even a vector of floats, we're having to define float twice. Now, if you're a good little programmer, that hurts you, right? You're like, oh, why are we saying that twice? Like, bad things can happen. And in fact, I'll show you how bad things can happen. Watch this. I can make this an int, and in some cases, I mean, an int might fail, but anyway, it's like, maybe not that one. It's all the is void stuff. I'm pretty sure there's some circumstances where you might be able to do that validly, where you have a container that's taking in a type T, but the actual, you have your class which is taking in a type T and storing it in a container of not type T. Like, so how do you constrain that? Now, I know you asked before, Kai, how do you constrain the types? This is a very specific example of that, and I'm sure you're asking broader. But this is a specific way of how you can basically, instead of saying float and a standard vector of floats, just say float and standard vector. Just give me the generic type, and like give the class the generic type, and it'll figure out that it's a standard vector of floats. You know, like it's cleaner, it's simpler, less room for error. So it's good that that's possible. The downside is that syntactically it's kind of a nightmare. And I kind of have this on the left here, right? I don't know why I went back to that example, but it's like, instead of saying a stack of ints and standard vector events, you just want to be able to say stack of ints and standard vector, stack of floats and standard vector. So how to do that is that we create template parameters. Now, the top example here, the top two are the example, the normal example without the template parameters, where we just simply say, okay, our class has a type name T and a container, and then we specify int and a standard vector of ints. The second example is when we use a template parameter, and we say, actually, we've got a template here which takes in a type name T, which is like our int or our float, and then it takes in a type name cont, which itself is parametered by something. And it's the same function, it does the same stuff, and the only other difference in the library that you'll see is that instead of just saying cont here, which used to be a whole type, like a standard vector of int or a standard vector of float, now we actually say cont of T. Now, intuitively this makes sense, because before we were like standard vector of int, so you didn't need the T. And now we're saying standard vector, so if you just think about copying and pasting it, it's like, well, we need the T now because we haven't specified what the type of the vector is. And this feels nice, right? Because this T relates to this T up here. So you've kind of got those two things joined in that way. And it does allow you to write simpler code like we've got down here. So if I go to, demo 8.10, template, I've already compiled this, it looks like, sometime a couple of weeks ago. It works. I don't think it does anything. Just pushes stuff, right? But it works. It compiles. Compiling's half the battle with this stuff. So that's really cool. Now let's take a look at what in God's name is happening here. So here's the way I think about it. It's like your template takes in... you have a class called stack. When you put template at the top of it, you're saying that this stack is a templated type. Takes in generics. It's a generic type. Then you give it the templates. When you say type name T here and this, you are now telling it how many templates it has. Basically, how many arguments inside the side brackets do you give it? 1, 2. So you're going to need 2 lines there. You're going to need 2 things between those side arrows. I've suddenly forgot what they're called. Yeah. So now the first one is easy. It's like, okay, there's 2 things I'm templated on. The first one is just a T. It's a random type called T. The second one is a random type called cont. So if you actually forget about this for a sec, it looks the same as what we had before. We're giving it two types. The only difference is by adding this at the start, you're actually telling it a bit more about what cont is. Here, cont is a concrete type. It's a fully resolved type. It's something like int or float or standard string or standard vector of t. It's a non-templated type, right? Like, sure, like standard vectors are templated, but this is a concrete type. It's not begging for more information to tell you what it is. It's like you've been clear about it. If you do a standard unordered map of ints and ints, it's like that's a fully concrete type. But like a standard unordered map is just still a generic waiting to be made concrete, and a standard vector without an int is just waiting to be made concrete. So if we want to use standard vector here, then we need to put out the front of this template type name. Putting template type name out the front, what it says is that cont is a templated type that has one type name. Now this will work for standard vector, right? Which I think is what we have here. Standard vector. Oh, no, it won't. Why not? Ah, yes. Okay, sorry. I got my data structures mixed up. But let me show you the problem here. So here's the problem. You think standard vector just has one templated argument, right? It just takes in that what it's storing. But if you actually go to the CPP reference, you'll see that templates actually are templated on two different types. Both the class T, which is the type you're dealing with, and a class allocator, which is kind of above my head, to be perfectly honest. But it's basically a way that it like, what is it? I remember how to explain this once, but it's to do with, yeah, I mean, the language, I can't summarize this better than the language because it's very clear. But it's how it essentially allocates resources. And there's a default one that you've probably never really worried about, and I've never worried about before. But the point is the vector takes in two templated types. Two of them. So therefore, to make this work, I have to say type name, type name. And that still doesn't work. What have I screwed up here? Too few template. Oh no, I've made a mistake. That's okay. The point is that this here actually, like, the point is that what this needs to do is this needs to reflect what the type name cont you give it is. So if you give the type name cont a standard vector, the template things on the left here need to reflect what a vector expects or something along those lines. So typically we get around that just by going template type name ... because just like variadic templates we saw before, this is a way of saying some list of type names. So now when I compile this, there could be one type name or two or three or four, and it will still work. Anyway, that's the whole background and rationale behind that. Super, I think it's interesting. Think I used that once in my life for something. Pretty random, but certainly interesting. Yeah, so that's pretty much it on template parameters. To loop back to Kai's question, how can I constrain my types so it only takes types you want to upcast or something? I still think probably the only advice I would be able to give, I mean, maybe there'd be more interesting people that could give you advice, is like, if you write your code such that only types that are safely upcasted are valid, then the compiler will handle those constraints for you by basically being a compile error, is the idea. So yeah, and then last thing in this course, Richard says, so since a vector expects two type names, you do this so you can use a container which may require multiple types to construct. Yeah, exactly. So the type name ... thing essentially says, like, whatever container we give it, if the container expects one argument or two or three, like if the container is templated across one type name or two or three or four or five or many, still make it valid. Of course, this though will only work for types, templated types, that only require one type to be made concrete. Because like an unordered map, for instance, an unordered map in C++, you can see here that an unordered map requires you to specify the two template types. But the way this code is written, you only have one to specify here. So you'd probably have to do like maybe that's another case of a partial specialization. Maybe, I don't know, but like the point is that this can work on any container type regardless of how many type parameters it has. It's just that only one of them can't be defaulted because like it's just not how you've written the library here, I guess. Yeah. And then lastly, just quickly on this topic, because some people have asked it before, there's this notion of template argument deduction, which is quite relevant, which is that what the compiler actually does is that the compiler determines the type of the type parameters and the non-type parameters, basically everything in the template line. It determines those by looking at the call parameters. Now, the call parameters are sometimes what we call arguments, which is that when someone calls find min, the compiler, if you don't tell it what generic types to use, it will actually figure that out from the arguments. And what we mean by that is that if you have a templated function here called f, which takes in a t star that you call array, arrays are pointed to a type t. When you created a c star array of ints and you say f of a, the compiler is like, what's a? A is a pointer to ints. Great. So then it looks at this and it says, all right, well, this can take in a pointer to something, and I have a pointer to ints, so therefore t must be an int. So I'm going to instantiate the int version of that. And the same kind of thing, works throughout here. It will do three. Okay, so the three. So that was just the example, but generally it wants to match the type exactly. The 3 times it will implicitly match it, though, are an array to a pointer, which is the example I just talked through, a non-const to a const. So as you can see here, A is non-const, but this actual templated type argument is const, but it'll do that conversion. And then the other one is derived, base types, super types, subtypes, just all the OO stuff that we're going to be talking about next week. Alternatively, you can always explicitly deduct things if you want to. This is kind of a... actually, so Physense just said, wouldn't it be better style to use implicit since it's simpler, or worse since you might lose some info while reading? Yeah, so in general, implicit deduction's okay unless you think you need to communicate that to someone. One thing you got to be careful of, though, is like if we have a templated function like min here, and we have a main function that creates an int and a double. If I call min with I, an int, and then I static cast d the double to an int, it'll, because I gave it 2 ints, template argument deduction will think t is an int in this case here. But if I wanted to actually tell it what I wanted to do with it, then sometimes the explicit deduction can be useful by saying min double here. I'm actually telling the compiler, can you go and instantiate a version of the min function where t is a double, and then I'll give you 2 parameters. One of them is an int, sure, but we know you can upcast an int to a double without a loss in precision. Yeah. So that's one instance where you might want to do like an explicit deduction, for instance. So these are just different ways of essentially like, these 2 ways you're getting the compiler to deduce it for you, and the commented outline here, and then this line here are ways of you telling the compiler, no, don't deduct it, I'm telling you exactly what it is. In this case here, this one's commented out because even though the compiler will try and instantiate a int version of this min function, the problem is that d is a double, so I think you get a compile error or a warning as an error that's like, there's a loss in precision here, because the double might be bigger than the int. But that's template argument deduction, and that is why you've been able to do things, and I think I've done this by accident, where you can say auto s equals standard vector 1, 2, 3, because the compiler's able to look at those ints and be like, well, yeah, looks like I know what the t is there. It's pretty unambiguous what the type is, so it'll just go and figure it out for you. Anyway, any last questions? Otherwise, we're gonna pretty much wrap up now, because that's the end of it. Should put up the feedback screen. Oh, I hope did I add the feedback in? God, I hope I did. I think I did. Yeah, I did. Okay, leave feedback. Thank you everyone for filling it in. I don't know how many people have been filling it in recently. I haven't really looked much. I mainly collect this at the end of term. Oh, feedback is sparse. Feedback is sparse. I'm getting like 2 or 3 a lecture. Thank you to whoever just filled that in. Average. How was the lecture? Average. Excellent. That's good. Cool. Thank you for that. Kai says in Java you can do generics like t extends n to say that you can only specialize templates that a subclass of n. Can you do that in C++? I don't know. Not that I know of, but I don't do a ton with templates regularly. So I'm not sure. Post that on the forum. I'll check with someone for you too. Cool. Yeah, I'm not too sure. I mean, the compiler will do it for you with some kind of specialization. But yeah, the compiler will catch it. I'm not sure if there's a more clear way to kind of signal that to someone though. But yeah, anyway, I'm going to wrap up there. And if you have any other questions, post on the forum. Otherwise, I'll see you tomorrow night. Everything else, nice to see you all and have a great evening.